Okay, today we're going to look at dma080. dma080, and we're going to start with section 2. Section 2 is looking at rational exponents. All right, now, last quarter we had dma070, which was rational expressions. And the thing about rational expressions was that everything we worked with was in the form of a fraction. So when you see the word rational along with the word exponent, guess what that means? That means that our fraction is going to be in the form as an exponent. So if we have a base that is raised to a power, and if that power is written as a rational exponent, the way that we would convert that into a radical expression would be A would be the numerator, M would be the exponent under the radical, the N, and the way I remember where the M and the N goes, the N goes here, and think about it, the word for the numeral here is called the index. So that's just kind of the way that I remember that. Another way that this could also be written could be in this form with the exponent on the outside. So this and this are both the same, but generally we're going to use it written in this format. One thing I do want to just go ahead and I'll show you right here on this one. This is going to be something that it will be like a test question for you. You may have something that looks like 7x plus 3 raised to the power of the 7/9. If you were to have this and they want you to write this in the form of a radical, you draw your radical. Underneath the radical, you have 7x plus 3. Now, I want you to notice there's a parenthesis around this. When you do your test question, we know the 7 would represent the exponent, but the way this is written, the 7 only applies to the number 3. Don't forget to put the parenthesis around it. That's the very important part because this is what's raised to the 7th. The index is going to be the number 9. And let me put this in color too. Oh. This piece here, you have to remember to put the parenthesis. If the parenthesis is not there, that's the usual problem when people do this question on the test is they forget their parenthesis. But it's really going to be a question just that simple. Now, before we get into doing a lot of complicated things with this, I'm going to start by giving you a couple of problems with rational exponents, and I'm going to want you to simplify these. And when we simplify these, I'm going to show you how to do these utilizing the calculator. Anything that has a number with a rational exponent, I definitely want you to use your calculator to do these problems. Okay, so let's start with the first one. 49 raised to the 3/2. So if you go to your calculator, you're going to do 49. Now, to raise it to the power, you may use the little caret key. And in order to do the fraction, I'm just going to do alpha y equals, choose number 1, and then type in my fraction 3/2. Whoops, 3/2. So 49 raised to the 3/2. If you have the older TI-83 and if you don't have, or the thick calculator and it doesn't raise to the power here, when you do 49 and the caret key, type the fraction in a parenthesis and it'll do the same thing. And then when I press enter, my solution is 343. Okay, for this problem, I would have 81 is going to be raised to the 1/2. So 81 raised to the 1/2. That's going to give us 9. And then for the x, remember, power to a power, you multiply. So 8 times 1/2 would give me 4. For this one, my -8 is in a parenthesis. So when we key this in, we have to put the -8 in the parenthesis. And the -8 is raised to the power of 2/3. And that gives me a +4. So as I said, you do not have to write these out longhand in radical form to solve. This particular one does not have a parenthesis, so you do not type a parenthesis when you do this one. So -27 raised to the, oh, raised to the 2/3. And that gives me a -9. 16 to the 3/4. Oh, hang on, keep hitting the wrong one. 3. And it gives me a +8. Now, for this last one, the only exponent is a 1/3. There is no parenthesis, so this 1/3 only applies to the end. So what I have here is 2m, then I'm going to do a radical. Under the radical is going to be n for the radicand. I do not need to write an understood 1, but I do need to put the cubed root here right in front. Another item to keep in mind, as we talked about in the previous section, is if we have negative exponents. Remember how if we have a to the negative n and we put it as 1 over a and put the n in the bottom? Same scenario applies here. If we have a to the negative m over n, that's going to be 1 over a to the m over n. It just means still it would drop down to the denominator, and then you would finish simplifying from there. So if we have, let's say, -64 raised to the -2/3, technically it is 1 over -64 to the 2/3. But if I'm doing this, I would type it in just like we see it here. So parenthesis, -64, and we're going to raise it to the -2/3. Now, it gives us a decimal. How do we change a decimal back to a fraction? Math, enter, enter, 1 over 16. So that will give us an answer of 1/16 for that one. Okay, so all of those types of things you can do using your calculator. However, we are going to get to some problems where we need to review our exponent rules. just to make sure you hadn't forgot those. The product rule is if you have the same base being multiplied, what do we do with the exponents? We add them. And in our case, we're going to be adding fractions. The power rule is if you have a power raised to a power, we multiply the exponents. And the quotient rule is if we have a division with the same base, we subtract the exponents. So we're going to still use those same three rules. It's just what the m and n's are going to be fractions. And when you're doing those fractions, just use your calculator to do your simplifying. Okay, so we have a to the 2/3 and an a to the 5/3. These are being multiplied. So what we're going to do technically is take 2/3 plus 5/3. I don't need you to have to do those longhand. All I'm going to want you to do is to use your calculator and add 2/3 and 5/3. And we're going to leave our answers with positive exponents. The practice here is just to be sure that we can do so. In this case, they have the same base, same denominator, so we can just add the numerators. So that's a to the 7/3. And for this scenario, we would leave it just as it is. Okay, let's try something such as this. Let's say we have, oh, wait a minute, my screen went away. There we go. Let's say we have b to the 1/2 and a b to the 3/4 over a negative b to the 1/4. The first thing we're going to do is we're going to add the 1/2 and the 3/4. So using your calculator, if you were to add those, 1/2 and 3/4 would give us 1/2 and 3/4 give us 5/4. Now at this point, what we do is we are going to have a positive and a negative. So what we have is a negative b, and then we're going to take 5/4 and we're going to subtract the 1/4. And 5/4 minus 1/4, that exponent here is 4/4. And what does 4/4 reduce to? It simplifies to be an understood 1. So our answer is just going to be negative b. You don't have to actually write the numeral 1 there. Let's do one more. Let's say we have y to the 3rd z. The entire numerator is cubed. And then let's say we have y to the 1/2, y to the 3rd, and then all of this is to the power of 6. What I would do is I would start with the numerator and do the power to power rule. So for the y in the numerator, we've got y to the 9th, z to the 3rd. The denominator you could do one of two ways. Either you could raise them both to the power and then add, or we could add the two together and then raise it to the power. I'm going to say let's go ahead and add the 1/2 and the 1/3. So if we add the 1/2 and the 1/3, that's going to give us 5/6. Now, when I do 5/6, the fraction 5/6 times 6, that's going to give me y to the 5th. And now we have in the numerator for the y, 9 minus 5 gives us 4, and then we have z to the 3rd. And that's all we have there. So when you're working with the rational exponents, you still have to use the rules of those. Now, You will also move into a fun process where we are going to have expressions. Let me start with a simple one. Let's say we have the 8th root of x to the 4th. In order to simplify this, I'm first going to write it as x to the 4/8. I'm going to take the radical and write it with a rational exponent. So let me make note here. Write radical with rational exponent. Then the next thing that I'm going to do is I'm going to simplify the exponent. So when I simplify that, 4/8 becomes 1/2. And then now what I'm going to do is I'm going to write back in radical form. So where we have this, I'm going to now put it back in radical form. So for this one, that's going to be radical sign x, that's the understood 1, and the 2 would be the square root. So technically for this one, we would just write the square root of x because we don't write the understood 2 nor the understood 1. But I'm wanting to show you the placement of where they would actually be. So the next couple of problems, that's how we're going to do these. Take the radical, write the radical with a rational exponent. Simplify, manipulate the exponent as needed. Then we're going to write it back in radical form. And that'll give you your final answer. Okay, so let's look at the 5th root of m to the 4th and the cubed root of m squared. So my numerator is m to the 4/5. My denominator is m to the 2/3. I just write them in radical form. My next step would be, with the quotient rule, is to subtract those exponents. I'm not going to make you have to write that out longhand. Just use your calculator and do 4/5 minus 2/3. So 4/5 minus 2/3 is going to give us 2/15. Oops. So give us 2/15. Now that we have it in the form of 2/15, we're going to come back and put it in the form of a radical. So m has an exponent of 2, and my index is a 15. Okay, let's say we have the square root of x times the square root, the 4th root of x. So in order to do this problem, I have x to the 1/2, because that's an understood 2 for the square root, and then I have x to the 1/4. Now, in order to do this problem, I need to combine these two. So I'm going to add 1/2 and 1/4. 1/2 plus 1/4. And when you add those, that's going to give you x to the 3/4. And then when we come back and put this in radical form, x is to the power of 3, and the index is a 4. Okay, the most complicated of these is you'll have a problem that you're going to work that has numerals rather than variables under the radical. So with a problem such as this, what we're going to do is we're going to start with writing my 2 is to the power of 1/2. My 3 is to the power of 1/5. Now, when I look at the two of these, there's nothing that I can do with this exact moment because the bases are different. When I look at my exponents, notice the denominators of the exponents are different. What I'm going to try to accomplish is I'm going to take both of these bases and I want them to have a common denominator. I'm going to use the denominator of 10. We know that 2 times 5 is 10, so 1 times 5 is going to give me a numerator of 5. 5/10 is equal to the 1/2. 5 times 2 is 10, so 1 times 2 is 2. 1/5 is equal to 2/10. Now, at this point, I can take this and put it back under the radical. My index is a 10. My 2 is to the 5th power, and my 3 is squared. So using your calculator, we still leave just the 10 here. We're going to do 2 squared. Actually, what is 2 squared? I mean, not 2 squared, excuse me, 2 to the 5th. I'm misspeaking. So we're going to do 2 to the 5th. 2 times 2 is 4. 4 times 2 is 8. 8 times 2 is 16. And 16 times 2 is 32. And then 3 squared, 3 times 3 is 9. So what we technically have is 2 raised to the 5th times 3 squared is going to give us 288. So my final solution is the 10th root of the number 288. Okay, so that is all of section 2. Now, as we look into section 3, section 3 is simplifying radical expressions. We started talking about this a little bit the other day when I showed you some of the calculator steps of simplifying some radicals. But for now, we're just going to look at a couple of basics before I move into the more complicated things. The square root of x over 9. I cannot take the square root of x, so that's just going to stay as a square root. But I can take the square root of 9, and that would give me a 3. If I have the square root of 2 times the square root of 8, they're both square roots. I can do 2 times 8 and get 16, and then the square root of 16 would give me a 4. If I have the cubed root of 4 times the cubed root of 16, what I'm going to do, since they are both a cubed root, I can multiply my 4 times 16, and that's going to give me 64. When I simplify the cube root of 64, I want to show you 2 ways. If you will do the index math, choose number 5, you have the cubed root of 64. That gives us the number 4. So the answer here is 4. The way I showed you the other day is that when you have a radical, what you do is you go to y1 and you type in the radicand divided by x, and the number you use for the exponent is going to be the index. Then you're going to do second table. You're going to look for a 1 in the second column. If there is a 1, it is a perfect root. It comes out evenly. If there is no 1, you still have to go to where the 1 would be and then scroll up looking for first pair of whole numbers. The number that's in column 1 is going to come out from under the radical. The number that you have in column 2 is going to stay under the radical, and you still put whatever index there may have been on that particular problem. So let me give you another problem that we can look at. Let's say I want to do the square root. Okay, this answer we said was, no, this was a cube root, wasn't it? Yeah, that was a cube root was 4. Okay, so let's say I'm going to do the cubed root of 320. So if I'm going to do the cube root of 320, I'm going to go to y equals, I'm going to type in 320 divided by x raised to the third power. So let's do that together. So 320 divided by x raised to the third power. Second table, as I look in the right-hand column, I would see if there's a 1. There is not a 1, but this is where the 1 would be. From here, I would scroll up, and my first pair of whole numbers is 4 and 5. So the 4 comes out, the 5 stays under the radical. So the 4 will come out, there's a 5 under the radical, and I still have to put the index here. Let's type in the other one, just so you can see one that has a 1. If we come back to y equals, and I do 64 divided by x raised to the third power, second table. For this one, when I look in the right column, there is a 1. And when there is a 1, it's a perfect cubed root. The cube root of 1 is just 1, so we don't have to write the radical. So when there is a 1, it's a perfect root, and the answer came out there as a 4. This little trick here that I'm showing you is something that I'm going to want you to use over and over and over again as you continue working with problems and simplifying. So let's say we have, and we're going to simplify the square root of 108 x y to the 7th power. What I would do is simplify the 108 using my calculator. So let's come back here. Y equals, clear, 108 divided by x squared, because the index is a 2. Second table, I look, and let me go down a little bit further, because you want to get to where a 1 would be. You need to see that in the next decimal to be sure it's not a perfect cube root, square root. So here's where the 1 should be. There's not one. As I come up, let your eye be here. This is my first pair of whole numbers. So a 6 comes out, and a 3 stays under the radical. So a 6 comes out, and then the 3 stays under the radical. Now, it's a square root. Remember, the index is 2. There's only one x, so that x is not going to come out. There's not enough. For the y, I would say 2 goes into 7 how many times? 3. 3 times 2 is 6. When you take 6 away from 7, you still have 1 left over. And so now I have simplified this radical into this form. Let's say we're going to do the square root of 27x to the 5th. Again, it's still square root. Y equals, clear, 27 divided by x squared. Second table, a 1 would be here, but there is not a 1. As I scroll up, 3 and 3 is my first pair of whole numbers. So a 3 comes out, and a 3 stays under the radical. The index is a 2, so for my x, 2 goes into 5 twice. 2 times 2 is 4. 4 from 5 leaves me with a single x. Now, in my next problem, I'm going to show you something a little bit different. When I write down this number, that number 3 is not an index. An index would be written little and up. This is a whole number. So if I'm simplifying this expression, I'm going to simplify this using the calculator first. So that's going to be 96 divided by x squared. The 1 would be here, and there is not a 1. So as I come up, notice there's 1, 2, 3 combinations. We have to choose the one coming up from the bottom, so the 4 and the 6. We could not use either of these because these are not reduced in their lowest form. This one is. 4 comes out, 6 stays under the radical. The 4 is a whole number. This 3 in front is a whole number. What's 4 times 3? 12, and then square root 6. Let's do one more similar to that. This is a whole number, not an index, in front with 12x cubed y to the 16th. So first I'm going to simplify that 12. Let's see, calculator. Okay, so we've got 12 divided by x squared, second table. Look for the 1, it's not here. My first pair of whole numbers is 2 and 3. So that means 2 square root 3. Multiply. 5 times 2 gives me a whole number 10. Under the radical is still a 3. Now let's start with the x's. The index is a 2. 2 goes into 3 once, and then there's 1 left over. For the y, 2 goes into 16 evenly 8 times. And now that expression is completely simplified. Let's do one more that has a cubed root. Now this is an index. Notice it's a little number. It's the index here. So we have the cube root of 24, a to the third, and b to the 10th. Okay, so for this one, we're doing 24. Let's hit clear. 24 divided by x raised to the third power. Second table, the 1 would be between these two, and my first pair of whole numbers is 2 and 3. So 2 comes out, 3 stays under the radical. Don't forget to put the index 3. For the a, 3 goes into 3 once, there's nothing left over. For the b, 3 goes into 10 how many times? 3 times. 3 times 3 is 9. And when you take that away, there's still 1 more of those left over. Okay? So one last thing, and I know you had wanted to be able to sort of touch on the addition and subtraction. So let's have a little conversation about that. Okay? So this is section 4. And it's addition, subtraction, multiplication of radical expressions. So when you have, let's say, 6 square root 5 minus 2 square root 5 plus 8 square root 5. When you look at this, I want you to get in the habit of seeing, for example, 6x minus 2x plus 8x. Do you see all three of these are a square root of 5? The index is the same, the number under the radical is the same, so they're like terms. All we're going to do here is combine our like terms. So for this, I'd say 6 minus 2 is 4, and 4 plus 8 is 12. So this one would be a 12x. But for this original problem here, again, 6 minus 2 is 4, 4 plus 8, so our answer here would be 12 square root 5. Now, we know they're not all going to be that simple and easy. So let's take one where we have 2 square root 24 plus 4 square root 54 plus 5 square root 96. Okay. Now, when I look at these, each radical has the same index but different numbers underneath. So what I'm going to do is use my calculator, and I'm going to simplify this part all at the same time on my calculator before I go any further. So let's go to our calculator, and we're going to start with 24 divided by x squared. Second table, and this is going to reduce to 2 and a 6. So that's going to be 2 square root 6. I'm not going to do anything else. I'm going to move here, and let's do the square root of 54. So on y equals, we're going to do 54 divided by x squared, second table. And the 1 would be here. Scroll up, we get a 3 and a 6. 3 square root 6. Now let's do the 96. So we have 96 divided by x squared, second table. 1 would be here. and 4/6 would be what we've got here. Once I have done that, now I'm going to continue. So 2 times 2 is going to give me 4 square root 6. Here, 3 times 4 is going to give me 12 square root 6. And here, 4 times 5 is going to give me 20 square root 6. Now, instead of having this complicated looking problem, aren't they all the square root of 6? Yeah. So this makes it really simple. We're going to combine like terms. So 4 and 12 is 16, and 16 and 20 is going to give me 36 square root 6. Let's do one that has a subtraction with it. So let's do the cubed root of 8x to the 4th plus 3x and the cubed root of x minus the square root of 16x to the 5th. Okay, so we need to simplify each of our terms. So let's start with the cube root of 8. Clear? 8 divided by x raised to the 3rd power. Second table. We have a 1. It's a perfect cubed root. So that comes out as the number 2. Now with the x, 3 goes into 4 how many times? Once. But I still have 1x left over. Don't forget to write the cubed root back down. For this particular one, I can't simplify any further, so that's just 3x cube root x minus. Now, we already know the square root of 16. That would be 4. For the x, the index is a 2, so 2 goes into 5 twice. 2 times 2 is 4. We still have 1x left under the radical. For this particular problem, when we combine like terms, only these two are like terms because these both have cube roots. The index here is the understood 2. So we're going to have a 2 plus 3, so that's 5x, and then cubed root x. This we just bring down, minus 4x squared, square root x. And with that, you are finished. Okay, let's do a multiplication. With a multiplication, the first one I'm going to do, we have the square root of 5 minus the square root of 2, the square root of 2 plus the square root of 6. I want you to remember and use the FOIL method when you're doing the ones that are 2 by 2. Here we have the square root of 5 times 2. What I would have here is they're not prime numbers, so we would have the square root of 10. When I do my outside, I've got 5 times 6. That's going to give me plus square root of 30. Here in the middle, I have a negative. Both of these are the same. So 2 times 2 is 4. And what is the square root of 4? I like to look at it and go, oh, they're the same. The 2 comes out from under the radical. And then here we have a minus, and 2 times 6 is going to give me 12. I'm still not completely finished. I would need to simplify and see if any of these could reduce. Now I know the 10 can't reduce. That's just square root of 10. The square root of 30 I don't think reduces, but I'm going to double check. So I'm going to do 30 divided by x squared. Second table. Look for a 1. And nope, it doesn't reduce because it's still 130. The other one we had was the 12. The 12, I do believe, is going to reduce. Yes, that was going to reduce to a 2 and a 3. So this one's going to be a 2 square root 3. This we said did not reduce. Minus 2 square root 3. So for this particular problem, we can't go any further. Let's do one more where we will have to combine some like terms. Or here, let's do it. We can do a distributing. Which one should we do? We'll do a distributing. Here we have the square root of 2 square root of 6 minus 3 square root 2. So if we're going to distribute here, that's going to give me the square root of 12 minus, now when I look at this and I distribute here, I have a pair of 2s, so a 2 is going to come out. So technically I have a 3. When you have two 2's, that 2 is going to come out as a 2. So when I first write this one down, I would already do 2 times 3, and I would have a 6. So when I look at this distributing, I personally don't write all of this down. I just wanted you to see what we're doing. This is the number 3. A pair of 2's comes out, and 2 times 3 would give me 6. We just simplified this a moment ago, which was a 2 square root 3, and then minus 6. And you would leave it there. Just to see if I can trick you on this one, when you look at something like this, if I give you the square root of 5 times the cubed root of 5, and if I asked you to do that, I would want you to let me know that they cannot be multiplied because the indexes are different. We can't combine them. The only way they could be combined is if I did 5 to the 1/2 and 5 to the 1/3, made them have the same denominator and went through that whole process. But just in general, to try to multiply, you don't multiply numbers when the indexes are different, only when they are the same.